Good morning, ladies and gentlemen. Today we're going to be working on section 3 of the work and energy unit, which is conservation of energy. Okay, conservation of energy. And again, when something is conserved, when we say that, what that means is how much of it you have in the beginning is how much of it you have at the end. Okay, so think about this prompt real fast. Two students at the top of a platform, and one chooses to jump off, the other one chooses to take a water slide. Okay, so imagine you're at a water park. You can either dive into the water or you can go down the slide. Okay, it's saying one steps off the platform and falls directly into the water. So someone jumps off the diving board or whatever. Somebody jumps. The other person takes the slide. Assuming the slide is frictionless, which one hits the water with the greater speed? Okay, so you have a diving board. Okay, you have something here. Okay, you have a diving board and you have a slide that goes down to the water. Okay, they both go to the water. Okay, and you have some water here, whatever. Okay, and you have two people up here. Someone chooses to take the slide, and the other person chooses to just jump off. Okay, which one's going to hit the water with the greater speed? That's the current situation we're in. The answer is they're going to actually hit the water with the exact same speed. In the previous section, in section 2, we talked about the two types of energy that we're going to be working with. We talked about kinetic energy and we talked about potential energy. When you jump off a platform, or when you're at the top of the platform, let me start there. When you're at the top of the platform, you're at the same height. Both students are at the exact same height. If they're at the exact same height, they both have the exact same potential energy. Okay. What's going to happen is that potential energy is going to get converted into kinetic. Because they have the same height and the same potential, that means they're going to hit the water with the same amount of kinetic energy. And if they have the same kinetic energy, they're going to have the same speed, assuming they have the same mass. Okay, assuming both students weigh the same. If the slide had friction, would that change? The answer is yes. If the slide has friction, when you go down the slide, some of your potential is actually being lost. It's being lost to friction. Okay, it's being lost to things like heat. Okay, some of it is being transformed into other stuff. Okay, but if there's no friction, whether you take the slide or you jump off, if you're going down the same height, you're going to hit it with the same speed. Okay. This we talked about. What does it mean when a quantity is conserved? Conserved just means what you have in the beginning is what you have at the end. And some examples. Okay, mass is an example of a conserved quantity. If you eat food, the total amount of mass in the system being you, your body, things like that, that it stays the same. Let's say you have some nuts, okay, cashews, peanuts, whatever. You have 50 grams of it. If you eat those 50 grams of cashews, it's inside of you. Your body's going to turn it into other stuff, but the mass is conserved. Okay, things like volume are not. Think of clay. Okay, let's say you have a certain amount of clay. You can stretch the clay and make it as big as possible, or you can compress it and make it as small as possible. Either way, you have the same amount of material, so you have the same amount of mass. But the volume is changing. Okay, volume is not a conserved quantity. Okay, so that's an example of one that is and one that isn't, other than energy. Okay, so here's a new term that you're going to learn. Okay, mechanical energy. Mechanical energy is the sum of the motion related energies. Okay, think about it like that. Mechanical energy is not a new type of energy, it is just a way to look at a system and determine how much of the energy is actually associated with just motion. Okay, so mechanical energy is the sum of kinetic energy plus gravitational potential, that's what the G is for, plus elastic potential. And remember that elastic potential has to do with springs and rubber bands. Gravitational potential has to do with height. I'm not gonna go through the practice problems because we're gonna do that on the sheet. Okay, but here's what I want you to get out of this. This table right here is important. I'm going to rewrite these numbers because they have it in reverse, which is not conducive to explaining what is actually happening. Okay, so 1 is still 1, and then this is 0.5. Then this is 0. Okay, so this is the top, the 2. Okay, this is the top, and this is the bottom. When you're at the top of the platform, 2 meters, let's say it's 2 meters. When you're at the top, what you have is you have potential energy. Okay, your PE is 19.6. Since we're not moving yet, kinetic energy is 0. As you fall, notice what's happening. The potential is being converted to kinetic. Okay, at the halfway point, notice the potential energy and the kinetic energy are the same number. Okay, and as you continue to fall, now you have the opposite of the 1.5. Notice how these just reverse. Again, your potential is being converted to kinetic. And once you hit the bottom, all your potential is gone, and now you're left with just kinetic. Okay. So what's happening is your potential energy is being converted to kinetic energy as you fall. But if you look at the total energy in the system, mechanical energy is the total energy with motion in the system. Notice how it does not change the entire time. It's 19.6 the entire time. Okay, which means no, you're not getting any new energy. You can't magically get it out of thin air. So what you have in the beginning is what you have in the end. That's conservation of energy. Okay, this is the example. Potential is being converted to kinetic, but the total amount in the system doesn't change. And this is just in equation form. MEI is equal to MEF. I is initial, F is final. It is just saying that the mechanical energy you have in the beginning better be equal to the final mechanical energy you have at the end, assuming there is no friction. Okay, assuming there is no friction. Okay, so kinetic energy and potential, they basically transform into each other. Okay, if you're falling, potential energy is being changed into kinetic. If you're going up a hill, for example, let's say you roll a ball and the ball starts rolling up a hill, in that case, you're losing kinetic energy and it's being converted into potential. Okay, that's the main point I want you to get out of it. And then this last slide right here, this is just some final points. For conservation of energy, acceleration does not have to be constant. If friction is present, then you no longer have conservation of energy. Okay, if friction is present, you no longer conserve energy. What happens to that energy? You lose it to friction. And what is it converted into? It's converted into non-mechanical energy, like thermal energy or chemical potential, depending on if we're working with chemicals and chemistry and things like that. Okay, but this is the main point. Okay, what I want you to get out of this at the end of the day is just know what mechanical energy is. It's just the sum of all the motion energies, and just know where it comes from. So the kinetic potential, gravitational potential, and elastic. Okay, that's really the biggest part of this section that I want you to get out of this. Is just that ME is equal to KE plus PE. Okay, this is what I want you to get out of this. Okay, this is what's the important part. Okay, now let's go through some practice problems. Where are we at right now? Okay, we're at 9 minutes. Okay, I'm trying to make this video shorter because I know no one likes to watch 30-minute videos. So I'm trying to work on the speed. I'm gonna go through 5, 6, and 7 of the conservation of energy sheet that does not have the key. Okay, so this is the one I'm doing is from day 6, the one without the key, like always. I'm going to do 5, 6, and 7. Okay. So in number 5, I'm going to set up 5. I'm going to try to do this quickly. In 5, here's what you have. It says motorcycle, but I'm going to draw a car because I don't know how to draw motorcycles. Okay, for the sake of just speed. Okay, here's your car. The car is going to go up the hill, and it is going to go 250 meters up the hill. I'm going to go back to the problem in a second. And the car itself is 250 kilograms, or the motorcyclist and the driver, or the motorcycle and the driver, 250 kilograms total. All right. So what you have going on is at the bottom of the hill. At the bottom of the hill, the motorcyclist reaches a top speed. Okay. Motorcyclist is at top speed at the bottom of the hill. So right here at the bottom, it's going as fast as it can go. Then it coasts up the hill. That coast is an important part, okay? Coasting up the hill means that your foot is off of the gas. It is just it's like a ball rolling up the hill. You roll a ball up the hill, it's just going to slow down. So it's coasting up the hill, and without pressing the gas, it reaches 250 meters. So once it reaches 250 meters, that's it. It's no longer moving. The kinetic energy that it had was transformed into potential. What we are looking for at the end of the day is, what was that top speed? We're looking for the initial speed of the motorcycle. We want to know what that top speed was. Okay? But in order for us to do that, we need to know how much energy is in the system. We need to find the mechanical energy. Okay? That's what we need to find. So let's do that. We're going to need two equations. We're going to need the PE equation and the ME, or the KE equation. PEG, to be more specific, okay, gravitational potential. So PEG is mgh, mass times gravitational acceleration, which you know is 9.81, times the height. And then KE, I'm writing this for reference because we're going to need it to answer the question. KE is equal to 1/2 mv squared. And this V is what we're looking for. Okay? The V is what we're looking for. So the mechanical energy in the system. We don't know everything about the beginning, but we do know everything about the end. So at the end, at the final, so after you go up the hill and you stop moving, how much energy do we have? Let's find out. So how much potential energy do we have at the end? That's where the mgh equation comes in. Let me scroll up a little so you can see it. So what is our mass? Our mass is 250. We need to multiply by gravitational acceleration, which is 9.81. Times the height. How high did we go? We went up 250 meters. Okay, this is the potential energy that we have now at the end, at the very end. Okay, normally I would say that's the end of it, and now we're good and we can solve the speed. But actually, that's not true because there's another note in here. Okay, it says that we lost a certain amount of energy to friction. We lost this much energy to friction as it went up the hill. So these three numbers multiplied is not going to give us all of the energy that we actually started with. We lost some of it to friction. How much did we lose to friction? It told us. So we lost 2.55 times 10 to the 5th joules to friction. Okay. So if you multiply these three numbers and then add this last number, you will then get the total amount of energy that you had in the very beginning of the problem, okay? At the bottom of the hill, I should say. That tells you how much energy you now have at the bottom of the hill. If you multiply those numbers out, you will get 868,125. So 868, 125. And now we can answer the question. Okay. This is how much energy is in the system. Now we can answer the question. We want to know what the initial speed was. If energy is conserved, the energy at the end should be the amount that you have in the beginning. So this is how much energy the motorcycle had in the beginning, too. So, and in the beginning, what we had was kinetic energy. So this is the equation we need to use. And we need to solve for V. Okay? I've showed you guys how to rearrange this equation a couple times, so I'm just gonna rearrange it and just use it. I'm not gonna show how. So the equation we have, after you finish rearranging that, you should have that V is equal to 2 times the kinetic energy, 2 times KE. That whole thing divided by M. And then you have to take the square root, okay? We know the mass is 250. You know the kinetic energy, it's right here. And then 2 is just 2. So if you plug all of these numbers in, divided by 250, and then take the square root of that, what do you get? You get that this is equal to 20,834.16, and this should be in meters per second. Okay. That to me seems kind of ridiculously fast. But it's the numbers they gave us. So you got what we got. This is one of those situations where I tell you look at the numbers and see if it makes sense. This doesn't make perfect sense to me. That's actually a lot of energy. But hey, what can we do? So this is your final velocity. That's your final answer for number 5. Where are we at right now in terms of time? Okay, we're at 17 minutes. Okay, it's not bad. Let's do number 6. In 6, you have a mine. The mine is 12.3 kilometers. Okay, so we need to convert that to meters. Suppose you drop a rock with a mass of 120 grams. We want to know what would the rock's kinetic energy be after falling that much, and what is the potential energy at that same point, okay? So here's a diagram. Okay, you have a shaft. Okay, you have a shaft. Okay, and the person, I'm going to say you're standing right here and you have a rock. Okay, and you're dropping the rock. The shaft is a total of, hold up, is that going to, okay, good. The shaft is a total of 12.3 kilometers, okay? So it's 12.3 kilometers. I'm going to convert that to meters, okay? So the shaft is 12,300 meters long. That's the whole shaft. We dropped a rock in there. We dropped a rock, and this is our rock. The rock is here at this height, okay? The rock only goes down 3.2 kilometers, or 3,200 meters. So the rock still has a long way to go. So the rock fell 3,200 meters. The whole thing is 12,300 meters long. What is the kinetic energy that we have right now? Just plug in the numbers. Well, actually, no, we don't know that yet. I'm sorry. We don't know what would the rock's kinetic energy be after falling 3.2. We don't know that. Not yet. We can't calculate it yet. We need to find the potential first. So let's do that. how much. There's a couple ways you can do this. You can do this with percentages, or you can convert simply potential to kinetic by looking at the initial system. I would say the easiest way to do this is to look at percentages, and you'll see what I mean by that right now. So let's find how much potential energy is in the system, period. So at the very, very tippy top, how much potential energy do we have? To get that, you just do mass times gravity times h. So the mass of the rock is 120 grams. You need to convert that to kilograms, okay? You need to convert it to kilograms. To do that, just divide by 1,000. So we have 0.12 kilograms. That's how much the rock weighs. Or that's the mass of the rock, not weight. Weight and mass are different, I'm sorry. So this is the mass of the rock. Gravity is, again, 9.81. And then the height. The height is 12,300. If you put that into your calculator, you're going to get a number, and that number is this. That number is this. So 0.12 times 9.81 times 12,300 is 14479. .6. 14479.6 joules. Okay, joules. So this is how much potential energy is in the system, period. Okay. We fell 3,200 meters. So if you do 3,200 divided by 12,300, that'll tell you how much you fell total percentage-wise. So we've fallen about 26% of the way there, okay? So we're about a quarter there. We're about a quarter of the way down the shaft, okay? If we've only fallen about a quarter, that means we've only converted about a quarter of this energy. Remember, if you go back to the slides, this table, this is the exact same scenario, okay? Oh, I went too far. Where's the table? Here it is. We start at a certain height. As you fall down, potential gets converted to kinetic. And at the halfway point, this is the halfway point, halfway there, half of the potential is converted to kinetic. So you can work with fractions and percentages when doing this. This is the exact same scenario. You have something falling, the potential is being converted into kinetic. So we fell about a quarter of the way there. So if you multiply these two numbers together, you're going to get how much potential energy was converted into kinetic. And if you do that, you get this. This times this. So our KE is now we know what the number is, we can answer the question. Our KE, after you multiply those numbers, is 3767. This is how much kinetic energy we have in the system. And that has to equal 1/2 mv squared. So now we can find the velocity. Are we even looking for the velocity? No. We just want the rock's kinetic energy, okay? So actually, no. I'm actually going to skip this. Okay, now we know. Now we don't need to find velocity. We're not looking for velocity. But now we answered the question. We know how much kinetic energy he's going to have. He's going to have this much. Okay, so this is your answer for that part. It also wants to know at that same point, how much potential energy is going to be left at that same moment. So at this same height, how much potential energy is left? You just subtract these numbers. So you subtract the 14,479.6 and you subtract 3767. If you do that, you get that your potential energy is, let me change colors. You get that PE is equal to this minus this. You should get 10,712.6. Okay, that's the answer for number 6. Okay, shaft is this tall. You drop a rock at this point. What's the KE? What's the PE? How did we do it? We found the PE total. Okay, this right here is how much potential energy you have at the maximum height. What we did was we found the fraction of the fall. We fell 3,200 out of 12,300, and we got our percentage. You multiply the percentage by your total, and you can figure out how much kinetic you have. And then you just subtract those numbers, and then you can find how much potential you have left. That is what we did in this problem. Okay, that is how you do number 6. What's the time on here? All right, and then I'll number 7. Well, at least the time is going into the practice and not the actual slides. So I only spent 9 minutes on slides, which is what I was. That's good. Last problem, number 7. Roller coaster. Okay, we like roller coasters, right? Okay. Roller coaster, vertical drop of 68.6. Okay, so here's what we have. Roller coaster, you coast up the top, and then you have a vertical drop. Usually it's not straight vertical. Usually there's a slight forward piece just so you don't die. But we know that the vertical drop is 68.6. Okay, this is what we know. Okay, so you're just a car or a roller coaster. Going up, and then you have your vertical drop at the bottom. Okay, 68.6. The roller coaster is designed so that when you reach the bottom, you should be going 35.6 meters per second. When you reach the bottom, that's how fast you should be going. Assume the cars are at rest at the start of the drop. So there's no initial speed. That's what it's saying. So the car is here at the tippy top and it's not moving yet. We just push it over and it slides down. It says what percentage of the initial mechanical energy is lost to friction? Okay. So what this is telling us is that this 35.6 meters per second at the bottom, that's not how fast it would be going if friction wasn't there. Okay. So if friction was gone, this number would be higher. But they know that with friction, it's going to slow down to this. What we need to find is how much of that energy is being lost to friction. In order to do that, we need to know how much energy is in the system total. To do that, we just got to look at the potential. So at the top, cars at rest, what's our potential energy? It's just mgh. Mgh in this case would be, well, do they give us the mass of the car? They don't give us the mass of the car. So in this case, this is going to require a little bit of finesse. Okay. So here, this is going to require some cancellations. Which we can do. So this actually might be a little more difficult than I intend, but let's work with it. Okay. Here's what we know. We want to know the percentage of mechanical energy that's lost to friction. PE is equal to mgh, right? And Ke, yeah, I wouldn't expect you guys to do this. This is actually more difficult than I intended. So Ke is equal to mv squared, okay? We know this. Now, here's what I need you to understand. At the top of this hill, you have all potential. And when you come down to the very bottom, you have all kinetic. The potential energy is supposed to be converted all into kinetic, okay? So if you set these two things equal to each other, if you do mgh is equal to 1/2 mv squared, you can actually get rid of the masses, okay? You can get rid of the masses. Now that the masses are gone, you can solve for v squared like this. Okay, rearrange the equation, you get that v is equal to g h times 2. And you just have to take the square root of that entire thing, okay? So if we just use the gravity and the height from the initial problem from the very beginning, this should give us a velocity without friction. So square root of 2 times 9.81 times 68.6, you get 36.7. So let me just work through what I just did because some of you might be confused. So at the top of the roller coaster, we're here, okay? Top of the roller coaster, we have all potential. At the bottom of the roller coaster, you know that all the potential is going to be converted to kinetic, right? So that means the potential energy in the beginning needs to be equal to the kinetic energy at the end, okay? So this is the potential energy initial in the beginning. This is the kinetic energy at the end. They need to be equal to each other. If I set the equations equal to each other, you get this. mgh is equal to 1/2 mv squared. But because you have m on both sides, you have mass on both sides, and it's the same car, so you can delete it. Okay, you can divide both sides by m, and now m is gone. And now all you have left is gh is equal to 1/2 v squared. And then if you solve for v, this is what you get. You get the square root of 2 times g times h. You plug those numbers in, you get a speed of 36.7 meters per second. Okay, you get 36.7 meters per second. Now we need to find what percentage of the initial mechanical energy is dissipated. Okay, so now I need some space here. We know what the velocity would be without friction. So the velocity without friction would be 36.7. The velocity with friction is 35.6. Now to find that final percentage, basically you can just look at what fraction did we lose. So what's the difference? This is what you would have without friction. We lost, let's see, how much of it did we lose? So you would do 36.7 minus 35.6. That's equal to, there should be 1 point or 0.9, is it? What happened to my pencil? Okay. So we lost 1.1. And if you do, now you can just fraction it. 1.1 divided by 36.7 is equal to should be 0. Basically 0.03. which is the same as 3%. Okay. So number 7 was a lot harder than I anticipated. So my apologies on that, because it doesn't give you the mass. Some of you may not know what to do if you don't have the mass, but you actually don't need the mass because the masses end up canceling out. Okay, so that's 5, 6, and 7. It goes by increasing difficulty. So 1 to 4 should not be as hard as 5, 6, and 7. D shouldn't have any tricks like that. I don't think they do. It doesn't look like it. All right. Okay. So that's it for conservation of energy. Again, if you guys have any questions, always ask. You can work with each other, use the internet resources. Okay, you have everything at your disposal. Okay. Wish you guys the best and take care.